Hi, this is Henk Akkermans and this is Supply Chain Dynamics Chapter 1, Sysdea Gameplay 2, a simple supply chain model. So we ended up here with, in the previous gameplay, with an amount of work, new work coming in at a rate of 500, going out at a rate of 500, while we have 1,000 capacity available, and that's of course a waste of money. So probably we want capacity to be less. Well, let's make it less then. Let's make that behavior endogenous, as we say. So I'll have a flow in here, which I can call change in capacity. Capacity change. Okay, but how will it change? Yeah. There are several options, but basically what we want is that the amount of work results in an amount of capacity required. Now, how much capacity do we need? Well, at any rate, we need as much capacity as we have work in here. But if we have more time than just the current period to do the work, perhaps then we only, so say if we have 500 but we have 2 weeks to do the work, then we really only need a capacity of 250, 500 divided by 2. So I'll add that also. I'll add a so-called target lead time to use supply chain speak. Let's make that indeed 2 weeks, why not? And let's put it in here. And then the capacity required becomes the amount of work divided by the target lead time. Nice. This then can become the input of the capacity change rate. So the capacity change rate can be the capacity required. No, because if we do that, then the capacity keeps growing all the time here. So we have to say, yeah, it's fine that you have 250, but actually we want the capacity here to become equal to the capacity change rate here. So we need this value also back in there. And what we then say, that the capacity required minus the capacity availability, that's what we want. So the net difference. This leads to a pretty chaotic behavior, and actually what we should bear in mind that if this takes some time, that the capacity change delay will also take some time. You cannot do these things instantaneously. So we'll have a more sophisticated formulation by having a capacity change rate as well in here of, let's say, 4 time periods. If I then put this in here, I will now divide the total required change by this, by the capacity change rate, but I wanted to measure it. And now you see, let's call this delay because that's what I wanted it to call. Now you see a very nice smooth picture here. It takes 4 weeks to adjust the capacity rate to the capacity available over this time delay, and isn't life wonderful? But what you also see is that there are some changes here in the we are not there yet. Let's see if we take a longer time period, or even longer still, then you see that somehow we are not being able to get this stuff smooth. Here in this graph you see both. You see that we keep oscillating between the amount of work and the amount of capacity available. Strange, because we gave a very clear signal. There's 500 coming in, we need 500. So we want the capacity to be adjusted to that 500. But somehow it's not working. And that phenomenon is called oscillation. And why is it not working? Well, because the capacity overshoots. So you would like it to be at 500, but you see that once it is at 500 up here, it goes down further. Why is that? Well, there are some delays involved up in here. So both in the change rate here and in the lead time there. And it will take us some time to clean up all this inherent instability. And we call that oscillation, and the coming chapters will talk more about